you look
Just like a
at
Chuck Pilsner.
50 years ago, okay, American wines. Now, a lot of it sucks off.
Oh, yeah.
When I was doing some.
I remember the Almond Dead Mountain Red days.
Oh, yeah, Gallo, Artie Burgundy.
I got Boone's Farm.
Mad Dog
That's what we used to have.
But the price was good. I'm not talking about the taste, but the
I
price.
guess where a lot of the best award-winning whiskeys and scotch are made now.
We're good. No
Right,
matter what
yeah, because they're trying to
happens,
make,
we're
yeah.
good.
Japanese whiskeys and scotch aren't as
You
good.
drink this Japanese
It's
scotch,
not a refined,
it's not the real
I
stuff.
like the peach stuff, I like the peach
I don't know how made this be with this total bullshit. The pure market burgers and the best. I believe it somehow.
Oh, that
Makes it taste better.
Yeah, scotch.
You know, we were
But how come is this true? How come the blend is not better than the
I don't think,
no.
no, I think it, they just make it.
They have unique
decently.
taste, they have
My
unique
job
taste.
is-
Johnny Walker's, so they make it taste the same.
Scotch,
But it doesn't. Pure one is better. How come? They made me, it's kind of propaganda. I lost my brain. I'm kind of brainwashed. I believe pure malt is better. I feel that it's better, but I can't believe it's true.
I love
You're out in Cancer Alley, right?
You're just so passionate.
Listening on my scotch, I'm passionate about my scotch. My scotch
They're
is
proper,
proper.
they're not really kind of a balanced blend. They all have a lot of peat in them, or sherry, or they all have their unique flavor.
Hey,
But
Rob.
the blends are all very
It
balanced.
must have been about maybe 20 years ago. We're visiting, our daughter was working at as a researcher at the University of California in San Francisco, medical research area.
Yeah,
So
yeah.
she's working, so my wife had said, well, let's go up into the wine country, okay? And she's an old Navy girl, so Christ, we're over the Golden Gate Bridge by 7:01 a.m., all right? So going up in the Sonoma, there's nobody in the hell in the open, and the town is totally closed down. So we're looking right about for coffee shop. Finally, we got there at 8:30 in the morning.
That's my home state, by the way.
I know, okay,
No,
no,
that's
wait,
salted.
wait a second,
That's salted.
Wait a second, so the Ravenswood Vineyard is open at 8:30, okay?
Yeah.
So we go in there, and there's this California guy there, he's got the haircut, he's got the bullshit. So he's talking about the wine, we're going in there, well, take this one, try this one, well, Christ, by 9 o'clock, we're half in the bottle, right now.
Yeah.
Bought a case of wine, and now we're gonna wend our way through into Napa Valley.
Yeah.
And we stop at, Christ, we stop at Arrowwood, go over the mountain, and we go down there, and we finally end up what's that? What's the town?
Napa?
And we're in the Napa, okay? We're Bergen, we're Behringer, okay?
Yeah.
So we go into this Tony restaurant, okay? But what the hell are we ordering? Wine.
Yeah.
Right. So we go there from there into Behringer's, okay? And by now we're basically a case and a half to the good. Right. So we're wending our way. Finally get our way down into between it's at the Silverado Road and the Napa Valley 29, the Silverado Road. There's a-
Silverado Trail.
Yeah.
Silverado Trail.
We got into the Rock Vineyard, which is one we really like, but back then we didn't afford it. And 4 o'clock, and now we bought a case. Now we got 2.5 cases of wine, okay? What the hell are we gonna do? You gotta ship it to yourself. They
Yeah.
don't ship it for you, so we.
Let me tell you something, Mark. 20 years ago, they would never charge anything for tasting.
Right.
Now every place,
Yeah.
it's at least $10 for tasting. It's incredible.
Yeah.
It's not. It's against God. It's really. It's not right.
God hates you.
No, it's terrible. So it used to be free. It was delicious.
Well, we were on a bicycle trip.
When you go drive it down, no questions asked. Understanding of the fundamentals.
I got yelled at here.
Maybe it's in Pennsylvania.
It's
I was
Yeah,
like,
it was like $10.
Chad's Ford Water.
Transport is horrible, but this one we went to was even more horrible.
Really?
But for me, it was.
You know what?
Can't grow
When I was
grapes.
a
No, did you
kid,
have this
Seriously,
experience a
they were
couple
going-
times?
They were making
I was
wine
working
and
on-
they dealt with grapes.
No.
Yes, I'm sorry, it should be from the
There's one
China.
down around Dover, actually.
Substituted ones.
Maryland's got
Yeah.
what's called
Yeah.
Rudy.
Both, Pennsylvania,
You know,
Delaware
maybe,
wines.
if, you
And
know,
cold
maybe that would
wines,
be a
German
big
wines.
number.
That's
Pure urine, it's sweet urine, it's not drinkable.
I love in the good old days, you would do the wine tasting.
What else we call it last year? Sweet urine, it's not drinkable. My love, it's not good for you, you're gonna die. California? Yes.
In the good old days, we would do the wine tasting, starting in Napa, and then you go up to Sonoma, there's those fucking switchbacks, so there's like,
I'll tell you what.
because it's, you have to
We
go through a whole
were,
bunch
we
of
were,
switchbacks.
we were actually, we did that, we were cyclists, okay? And up on the top is a Hessian,
Talk, because he's
Yeah, the
getting drunk,
Hessian.
look at him.
Whoa.
He's
Well,
drunk, make him talk.
that was a one, that was think about the Hessian. That venue and the upstairs is one of the best modern architectures. I mean, there are motherwells
waiting for her.
there, there are basically.
As soon as she's ready, she's gonna
I mean, that was actually, we were actually for the number of modern art collections in the Hess.
You know, we transfer
Vineyard.
metallics.
Well, that's the owner's.
Yeah.
Yeah, but I mean, it was available to
Like
you.
on
Yeah,
fire.
Roman, I think Aaron needs a,
So you use
it should be Sarafinas.
Yeah, I can.
Sarafinas,
He's doing
this
it
is-
upscale,
yeah.
so he will roll signs. So he possibly
You people don't know history.
Oh, my
Lithuania, the king of Lithuania became Polish king in 1796. In 1410, Jagiełło won the major war in Eastern Europe of the last year. And Poland and Lithuania was united for 700 years.
That's something to do,
Just
you
yourself.
know, coming back
Yeah.
into, well, the subject he was where.
Even with all the libraries, if I had.
not well trained,
He
and
was
properly
involved
involved.
with some queen of Poland.
Oh, she was exceptionally fuckable, let me explain.
Whatever you say. So, anyway, I just
I
got
saw the
back,
pictures.
I just got back from Toronto. We visited as many ethnic neighbors as we could. We went to the Eastern European one, and there's this one, Sarafinas, in Toronto. Have you been there? Oh, it's a great,
Yes.
nothing but Polish restaurants, the delis, all these pickled things.
You should be able to-
All
It's
seven
good,
campuses
yeah.
have a very
Everybody
entire
in
safety,
sidewalks is speaking Polish.
program,
It's great.
medical hygiene program.
People
All
are
the
showing up, so I
SOPs
guess
and
the union
There you
will
go.
find
gotta
out.
be
With
very
my
well
workout
so
saying
they
it
brought
has
in
sent
some very efficient consultants.
obviously.
Very
Only one way they can get here.
Yeah, right.
Aaron, my friend who was a Lithuanian, when those guys would travel across country, they didn't have a place to stay, we start looking for
No,
names
no.
ending in IAS
Sometime.
and call
Got guys
it.
that-
It was that good.
Oh, yeah.
I said, man, I'll change my name to IAS and call it.
Okay, well,
But I'll show you how,
Well,
yeah.
it's some I could easily include in the treasurer.
Funny, what does
I mean, Ron's got an almost Polish name.
It's ending, I-N-E.
Jimmy Biofsky with that repeat.
You ready?
Can they?
Actually,
You ready?
it is,
Showtime.
Okay, hello. So, I wanted to welcome everybody to the first talk for the 2019-2020 season for the Chemical Consultants Network. The CCN is a topical group of the American Chemical Society Philadelphia section, and we serve the chemical community by helping consultants launch their businesses or grow them. And in addition, we informally try to help people who are, let's say, in transition in between jobs, and anything we can do to help folks that are chemical professionals, we try to do that. Before we start, are there any folks in the audience who would like to introduce themselves that are new to CCN? Please.
Hi.
Sir.
My name is Joel Shurtak. I've been in consulting for about 4 or 5 years now, but this is my first meeting of the CCN. I do process development, process scale-up. I'm a chemical engineer by training. spent 40 years in the industry in specialty chemicals, commodity chemicals, carbon fiber composites, biotech, membrane filtration. I switched my career every 5 years by necessity, not by choice. And have my own independent consulting practice in Newark, Delaware. Again, commercialization startup. I'm thrilled to be here. Thank you very much.
Thank you very much. Ira? Please.
I'm Mark Siegel. I've also switched my career a lot. I'm from Newark, Wilmington, Delaware. And I'm a biochemist, an enzymologist initially. Did my PhD over at what's now Drexel University College of Medicine, postdoc University of Delaware. Then I've done some teaching for a while. I taught on the college level, taught on the high school level for about 6 years. And now I finally decided that I really wanted to return to scientific research. So I just began a postdoc position in environmental analytical chemistry at Villanova University. So again, I've done a lot of switching. Very, very nice to meet you all.
Thank you for coming.
Thank you.
Ira, would you like to?
Okay. Hi, Aurora. I've been a member for many years of the Chemical Consultants Network, but I've been a occasional attendee, I guess. I have worked mostly on the issues of extracting value from biomass, from pulp and paper side streams, particularly from lignin. And we just have installed a plant in Brazil to recover 20,000 tons of lignin, and now we are looking at applications and commercialization of the product. So that's what we are.
Okay, thank you very much. Okay, I think that's most of our newcomers.
Probably making a little rough and
So today we're privileged to have as our speaker our own secretary. In fact, all of our officers are here. I'm Keith Wing, I'm the chair, but Aaron Sarafinas is our secretary. And just by way of introduction, Aaron got his bachelor's in chemical engineering from Northeast University in Boston in 1982, his master's in chemical engineering in 1986 from Villanova. From 1982 to 2009, he worked at Roman Haas Chemical Company, where I actually had met Aaron. And it turns out that he spent 9 years each or so in ion exchange, ag process chemical engineering, and then in the Engineering Technology Center. And while he was at Roman Haas, he achieved the position of Technical Fellow and Distinguished Engineer. About 2009, Roman Haas transitioned to Dow, where he was working core R&D. And from 2009 to 2018, he worked in advanced polymer research. Recently, Aaron has transitioned over to becoming a consultant in engineering and chemical engineering. Today, he'll be talking about mixing sensitive reactions, recognizing them and dealing with them. And we realize that Aaron's a very, very talented engineer, and we're very, very pleased to have him speak with us. Aaron?
Thanks, Keith. We'll see if everybody's applauding as we go on.
No.
All right. We will. Okay. You got a brief introduction for me. We're going to do some brief demographics while the camera gets adjusted so you get the change in height. Who here is a chemist? Okay, we have about more than half the room for the people online. How many here are engineers? I'm amazed that we have almost half. And how many want to identify as something else? Okay, no. Now, who here has ever taken a process to a different scale? Okay, we have maybe half the room. And I can read this because, well, I've been to the optometrist. Who here has never had a problem scaling a process up or down? Oh, yeah, right.
It is true.
It is true.
It actually is true, only because I worked well with my engineers.
Ah, because you worked well with your engineers. We have another person who never had a problem scaling something up or down.
I never had to scale.
Never had to scale, okay. So, Who here has ever set the mixing for your process, either using the Goldilocks method that it looks good in the flask as it's going around, or using some other non-visual technique? Okay, we have maybe a third of the people. All right. Now, I believe that process development is a discussion, a dialogue. So I expect with this group that you'll be sharing some of your opinions tonight. Okay. So, well, I'm much taller in person. Why should you listen to me talk about any of this stuff at all? Well, I did spend 35 years with Roman Haas at Dow. Really, I'm a process development person that happens to specialize in mixing technology. And we'll talk about the process side of mixing today, because really good mixing, because Aaron, some people come up to me and say, Aaron, I need a good mixer. Well, good mixing is impossible to judge unless you know what the proper process context is. I started working on mixing early in my career on suspension polymerization systems, then in multi-phase reactions in ag, and then developed some expertise in simplifying processes and given various technical presentations, and we'll talk about some of the other things too. Well, we know what this term means, elected to retire from Dow in 2018.
Congratulations.
Thank you. Or as you said one time, I graduated in May 2018 to become a consultant who's looking to go and help clients achieve faster process development and more reliable scaling and leverage some advanced mixing technology. Really gets back down to doing some experienced problem solving. And there's a handful of things that I deal with in terms of helping folks troubleshoot and develop processes faster, simplifying and improving processes, managing technical capabilities, as well as delivering technical training. In a couple of weeks, I'll be giving a course on scaling and piloting in the process industries for Center for Professional Advancement. But today I'll be talking about the topic, does mixing matter? Well, prove that it doesn't, okay? Back in 2003, I was one of the organizers of the inaugural AICAG Process Development Symposium. And Ed Paul, who was a mixing expert from Merck, gave a tremendous talk about process development for APIs. And he came to a slide where he talked about any rules about mixing, and people are expecting, oh, we're going to get the secret. Well, the secret is always assume you have a problem with mixing until you prove you don't. And today we'll talk about how you prove you don't, or when you might think that you could have a problem. He has another one, scale up will make it worse. And actually, I used to have those two things as the tagline at the end of my emails, and back at Roman Haas and Dow. And in fact, when I elected to retire, one of my engineers went and put scale up will make it worse on a dozen golf balls. And we'll talk about addition on the surface or subsurface. By the way, for those of you who like to do work in the laboratory, let me rephrase that. For those of you who do work in the laboratory, do you like dripping things on the surface, or do you like having a dip tube in there? Who likes dripping things on the surface? Does anybody like a dip tube? They plug, they're awful. Well, they can have some benefits, and we'll talk about how we can judge that. Okay, so what am I going to do with this presentation? I'm going to start with a very simple process. A simple competitive reaction. We'll talk about relative mixing rates and reaction rates. We'll look at a sanitized process that will look familiar to one person in the room, well, two people in the room. I hopefully am familiar with it. And we can express our concerns about that process and say, well, wait a minute, I might have a concern about mixing on this process. Talk about some reactions from the literature where mixing intensity can drive reaction selectivity. And we'll talk about a simple experimental protocol that I've talked a lot about in other webinars, the Bourne protocol. Yes, we will tell all the jokes that go along with certain novels and certain movies, and I will show you the star of the Bourne protocol who does not look like Matt Damon. Anyway, we'll wrap up with some thoughts about where I'm going with next on this. All right, this is not an overview of mixing technology. If you want an overview, yeah, one thing that I've done a lot of as I started this consulting business was give webinars. Recently I gave a 3-part webinar for Dynachem that's available from Dynachem Resources. Yes, here's the way to get to it. The slides will be on the website in a PDF. The links will be active. But I will mention some mixing references. This will not be a detailed review of the Bourne Protocol. There are a couple of webinars about that. If you really are interested in it, go to the one for Scientific Update. But I'll talk about how this protocol can go and efficiently get you to understanding whether mixing is important or not. But we are going to start with a quiz. Oh, you studied, right? I will go and say there are two excellent references that are part of my wellness program. I can go and curl these, I can put them on my legs, do leg lifts. The Handbook of Industrial Mixing and Advances in Industrial Mixing from the North American Mixing Forum of AICHE. If you want to get one of these, or if you want to make friends with people with one of these, make sure they have this one, the Advances one, because it has the DVD in the back that has a full copy of Handbook of Industrial Mixing with all the corrections. Yeah, okay. Yes, they're heavy books. I'll also be tapping on an excellent paper by John Bourne, yes, that John Bourne, on mixing the selectivity of chemical reactions. And I'll walk back and get my mouse. I hope you studied for the quiz and you read these books from cover to cover, because here's your quiz. When you're scaling a chemical reaction system, a mixing system in general, what are the 3 scales of interest? No, don't shout out your answers. Hold them in your mind, because I will ask for answers later on. Have your answers? Good. I'll come back to this. We're going to start simple. Series parallel reactions, or competitive consecutive reactions, depending whose textbook you had for chemical reaction kinetics. We have A plus B going to R, which is the desired product. We have R plus B going to S, which is the undesired impurity, because anybody can make S. You just throw in a whole lot of B, right? You minimize losses to S by getting the charge appropriate. All right. So, what else can we do? Well, what about the order of addition? If you have A plus B going to R, R plus B going to S, and you want to minimize S, do I want to add A to B, or do I want to add B to A? B to A. Because obviously if I'm a drop of A falling into a puddle of B, I react to form R, and I look around and all I see is B. Oh, okay, I'm going to react to form S. All right. The bottom line of this simplistic example is having more B around is going to give you the undesired impurity. All right, so what the heck does that have to do with mixing? This is elementary, even for a chemical engineer, okay? The chemists are going, yeah, we knew this for a long time. Well, this has everything to do with mixing, because we're going to be talking about concentration gradients. High local concentrations giving you selectivity problems. And mixing is the way to overcome those concentration gradients. He says, hopefully. So here's my favorite definition of mixing. It's a process operation where mechanical energy induces fluid motion in a volume of fluid. Well, that's nice. We did that when we were babies in the bathtub and splashed our parents. Why do you induce fluid motion in a volume of fluid? To reduce inhomogeneities in fluid properties. Okay, that's nice. But why do you do that? You do that to achieve a process result. And what fluid properties are we talking about? Well, we're going to talk about concentration and temperature, but you could also have physical properties like density and viscosity, or quality of multi-phase mixing around suspensions or drop size. Okay. I'm going to show a video. It's a video from the BHR Group FMP Consortium. The folks online, sorry, I'm contractually obliged in my role as an FMP consultant that I can't, since we're recording this and it'll be available on the website, I can't have this video reside on the website, but I can show it to you, okay? We're going to look at some still images, and that's what the people online are seeing right now. So hopefully we will go and start. We have a 1 foot diameter tank. The impeller inside is about 1/3 of the tank diameter. It's a hydrofoil, high efficiency impeller. We're adding an indicator solution, which we're going to blend homogeneously in the tank. have 4 flat plate baffles in the tank. This is water, it's low viscosity. And eventually we're going to see a guy come over with a beaker that's not a large volume, and just like we're doing a titration, he's going to add something to make the indicator disappear. Just like I said, he's going to come over and he's going to pour this, there we go, okay. Now let's watch the indicator disappear. It all went away instantly, right?
Yeah.
No, it didn't. And you can see that we have regions of low concentration and high concentration. All right? It went away in about 16 seconds. This is what the folks online saw. We're going to take a look at the colorization and decolorization. Half a second into that addition, we had, wow, half a second, that's pretty quick, but look at the differences. Now I want you to think, well, what's the mixing time? Hey, this is a pretty high concentration. If my reaction's really fast, I might be worried about this sort of system. Similarly, a second into this, we see that we still have gradients. One cool thing about these images is that we do see some regions where you can look at the complexity of the flow patterns, and 1.8 seconds in, you still have some regions that have not seen the indicator. Some mixing software and some people believe that simple two-dimensional structures can give you information about the flow, but really, when you look at something like this, you know that it's more complex than the grand averages that people might show with 2D streamlines. So, we talk about half-life of reactions, right? Well, I'm going to talk about the half-time of the mixing. It took 16 seconds to blend. Well, what did it look like at 8 seconds? Huh. We have some regions that are relatively clear, some regions that are not as dark as what we had initially, but they are still having a substantial concentration of the indicator. Bottom line is we have to think about how our process can be affected by local concentration gradients. And if your chemistry is fast enough that you can still have something going on in this system to give you that bad stuff we were talking about, you need to worry about it. Sir?
Is that a function also of what type of mixer you're using for that particular point?
It can be.
Okay.
And I put at some add-on slides, that I can go back to. I can use different devices to create different degrees of intensity, and we'll talk about that. All right. Does mixing affect reactions? Well, the answer is sometimes, because if we look at this first reaction, we look at a simple rate expression for it. Does mixing affect the reaction rate? Well, what are chemical engineers taught? To quote Levenspiel's book on chemical reaction engineering, when he was talking about steady-state mixed-flow reactors, he said, but since the composition is uniform throughout, he goes and makes the math really simple. The reality is, composition is not uniform throughout. And in fact, if we look at the grand average in the tank, there's not a thing that mixing is doing to any of those parameters. The average is the average. What mixing is affecting is the local reaction rate. Well, what gradients can I have? I can have temperature gradients in the tank if it's an exothermic reaction. I can have local concentration differences, as we saw in the video, either from the blending that we were seeing or mass transfer. So let's take a different look at this and say, all right, I've got a feed tank of B with a solvent going into a bulk liquid that has A. I have the same two reactions. And I have a feed zone that kind of represents that blob of fluid that we had when we dumped in the indicator. Now we've got our two reactions, and if the first reaction is slower than the second reaction, well, as soon as I make R, it's going to react to form S. But in this feed plume where my concentration is high of my added reagent, if my first reaction is faster than the second reaction, I could have mixing sensitivities. I could get a different product distribution depending on how intensely I can rip apart that feed zone. All right. Here's a sanitized example from a paper I gave several years ago at AICAG. This may look familiar to one other person in the room, where we want to make this particular molecule from these starting materials. Okay? Anything worry you about this particular reagent that I'm going to react with an acid chloride? Two amines. Okay, there's a primary amine and a secondary amine. So let's think about this, and well, you know what? Which of these amines do you figure is going to react first?
The primary.
The primary, right. This one's going to go first. I want to make this sort of thing. So I want to react this compound, the B acid chloride, with this difunctional amine. So let's look at the first reaction. Okay, we've got A plus B goes to R, A plus B goes to R. Okay. The engineers in the room know the answer to this because we've all lived through it. What's missing, chemists?
Hydrogen chloride.
Hydrogen chloride. Some chemists, well, let's put it this way. Engineers are used to getting things that aren't balanced. Hydrogen chloride are missing and there's a heat effect, all right? Where's that hydrogen chloride going to go in this system?
Comes by the amine.
Goes back to the amine. Oh man. Hey, look at that. I'm making a byproduct that's consuming the reagent that is giving me excess B. Oh, we ought to do something about that, because if I go and look at the next reaction, I can overreact and make this B substituted material, and again HCl is missing, there's a heat effect there, and that's got, oh man, that's going to consume another of my amines. Huh. Well, the people who worked on this process did add an aqueous base to consume the HCl byproduct. There was an organic solvent that this particular reaction was being run in. So some things we need to worry about are hydrolysis of the acid chloride. And we also have to worry about hydrolysis of the organic solvent. All right? Again, when I teach this to engineers, don't forget about the HCl. We also have another reaction that can happen. We said that the primary amine was favored, but you can still get reaction in the secondary amine. And some ways we go and deal with that. We can deal with that in terms of temperature and concentration. In this sort of system, we worked at low temperature to go and make sure we control the amount of reverse isomer that we made. Again, this can overreact and make the diacylated impurity. Oh yeah, there's HCl that comes along for the ride there. This sort of system, there was concern that mixing could be important. Not only because there was this series parallel structure and we could worry about the concentration of B, but also because of mass transfer effects, because now I had an aqueous base and an organic solvent. Conceptually, what goes on in these series parallel reactions, again, I initially come in completely segregated in the feed zone, and I will go, and if I have slow or poor mixing, I'll only make, well, I'll make R, but the R just sees B, and that will react to form S. I'm going to introduce a term here. XS. XS is the fraction of B that goes to the bad stuff, goes to S. And in this case, all of it went to S. XS is 1. Flip it around the other way, and if I have perfect mixing and I have a checkerboard going on here with my A's and B's instantly being mixed or being mixed much faster than the reaction time, then I'm only making R, and in the limit, this XS goes to 0. Okay, well that's nice. We can figure out what our yield is on B, but what can I do with this? Damn Kohler numbers. and chemical engineers love dimensionless groups. Except this guy, Dan Kohler, was a rock star chemist in the early 1900s, and he looked at reaction rate relative to diffusion rate. Engineers said, oh man, I could come up with a whole bunch of Dan Kohler numbers. And the mixing Dan Kohler number is how long does it take to mix divided by how long does it take to react. Okay? And so some people have studied this to say, when do we need to worry about mixing? Well, think about the number 1,000. If the mixing is 1,000 times faster than the reaction, you don't need to worry about the mixing. If the mixing is 1,000 times slower than the reaction, you have a mixing sensitive system. If it's in between, it could be both. No matter what, unless the reaction is 1,000 times slower than the mixing, you need to worry about what's going on with the mixing. Okay, now, how did you do on the quiz? I want to know how many people said that the 3 scales of interest are the lab, the pilot plant, and the plant. Raise your hand. We have half the room who are honest souls. Or maybe the other half have heard me talk before. It's not the lab, pilot, plant, and plant. Because one person's physical pilot plant could be another person's production unit in terms of scale. The 3 scales are the macro scale, the meso scale, and the micro scale. The macro scale is what we looked at in that tank. It's the scale of the stirred tank itself. We're trying to make compositions uniform at the scale of the tank. And when I spread my arms out like this is the diameter of a 2,000 gallon vessel. Okay. The micro scale is what we were talking about at the molecular level or the particle level, where we're looking at the scale of the molecule, the flow is no longer convective, okay? The mesoscale is in between. It's that feed zone. It's that initial plume of indicator that we added that we could see in that first half second. That's the feed zone. That's the mesoscale. It's everything in between. So these 3 scales really allow us to think about what's controlling our process and think about mixing rates relative to reaction rates. All right, so I talked about Dan Kohler, but you know what? There's a problem. I saw some people sitting here going saying, yeah, I don't know, mixing rates, reaction rates. What mixing rate do you use? You just told me 3 mixing rates, and you showed us 16 seconds for that one blend time example. How do I go and figure out meso mixing and micro mixing? And on top of that, what if I don't know my kinetics? What if I don't have kinetics? What if I have something else going on that's a phase change, like a crystallization or precipitation? How can I determine my competitive rates that are going on in my process? Well, that's where the star of the Bourne protocol comes in, John Bourne. No, that is not Matt Damon. But it is a picture of John Bourne stolen. Very similar, thank you. Stolen from the 14th European Mixing Conference in Warsaw in 2012. He wrote the definitive review paper on mixing and chemical reaction systems, mixing and the selectivity of chemical reactions. They have a nice fat book that costs a lot on the same topic. It's a tremendous review article that talks about examples on single phase and multi-phase systems, as well as a protocol that we'll talk about. So, a lot of words here. I'm going to summarize. Bourne had 4 reactions that he looked at. A couple of them were looking at different substituted naphthols with diazotized sulfonylic acid. A couple of other ones were looking at a fast neutralization versus hydrolysis. Okay? And some of these reactions are used to go and characterize the mixing environment for different reactor configurations. And there are other reactions that have been used also. So what does Bourne do with these? We're going to look at that yield loss on B against feed time and against different agitation intensity. Okay. If mixing is a function of the feed rate, if when I feed slower, I get better yields, that is meso-mixing control. What's going on in that feed plume is important. If it's independent, if my yield on B going to bad stuff is independent of the feed rate, then I'm in the micro-mixing control regime. It's mixing at the molecular level that matters. Okay. Well, that could be useful. In fact, these different reactions have different ways of looking at it, whether I have another compound, like these being the hydrolysis type reaction byproducts and these being these series parallel type systems. And there are practical aspects of doing these that are covered in the Handbook of Industrial Mixing. Many years prior to Bourne's article, at Roman Haas, we had a system, the sanitized process, where we calculated that yield on B for we actually went and ran the experiment under certain mixing conditions and got this yield on B. We ran the first Bourne reaction. Then we also ran our process in the lab under the same condition. And we saw our S impurity going up as our mixing got worse, but we saw no change in the reverse isomer. It ended up that we did the same experiment, that being the royal we. Other people did the same experiment at the pilot scale and got the same sort of results. And when we ultimately did take the plant scale reactor, we got down to 1% reverse isomer. Partially because of mass transfer control, partially because of the micromixing control. Now this second reaction, again, well, you know what? Here's, for the chemists in the room, here are the relative rate constants for one of Bourne's set of reactions, the second Bourne reaction. And you can see we have orders of magnitude difference between the reaction rates. Now, again, do you know the kinetics of your process as well when you're doing screening studies and process development? I would be shocked if you did. Why use a model reaction system and do the calibration? That was a whole lot of data points from Bourne's data and from the Roman Haas data that went and, you know, looked at whether we were going to have a mixing issue. And what if the competing rate process has some challenging kinetics or is it a phase change? Well, that's where we get into this Bourne protocol. This is going to be looking incredibly simple. In fact, embarrassingly simple. But for those of you in the laboratory, when you set the agitator speed by eye, do you know what the agitator speed is? Not necessarily. It looks good. What Bourne says, and these types of experiments can be done at the laboratory scale or the pilot scale, first thing to do is impeller speed sensitivity. And what I like to do is have a wide range of speeds, maybe 100-fold difference in the amount of power that goes in. Wow, that sounds like a big difference. Can I do it in the same vessel? Well, you're talking maybe a factor of 4 or 5 on impeller speed to do that. So maybe you're running at 150 and 650 RPM. If you see no difference, you stop. You're done. There is no mixing sensitivity. But if there is a sensitivity, then you look at feed rate. We're going to change the way that feed plume works. Bourne says if there's no sensitivity, then hey, you're controlled by what goes on, the molecular size. If there is a sensitivity, he says, look at that feed point sensitivity. I'm going to say he also had some confirmatory experiments where you can look at the number of feed points and the viscosity. Viscosity is really a practical thing to look at for an industrial process. Number of feed points we have looked at extensively. And if we look at his original data, if I increase my impeller speed, I actually improve my yield on B, lowering the yield to going to the wrong stuff. If I look at feed rate, I could have a mixing sensitive region or I can have a mixing insensitive region depending on what flow rates I choose that make sense relative to the plant process. I can look at feed locations, and again, it's kind of like changing impeller speed. If I get closer to the agitator, it's more intense. And I should get less B going to the wrong stuff. Number of feed points, well, you're looking at local velocity effects. And you can either make better material at the same feed time with more feed points, or I can improve the quality and actually decrease the feed time at the same yield on B. Okay. Scaling this stuff up, we keep power per unit mass constant. For micro mixing control, for meso mixing control, it's challenging because, well, maybe I just have to beat it up a lot, Bourne said. Or maybe I have to feed a whole lot slower, Bourne said. But the crystallization literature is saying something interesting. Crystallization literature says I look at the ratio of feed time to meso mixing time. And then macro mixing control, that's the blend time thing. Maybe we use, high efficiency impellers or static mixers. So why does this work? If Art Etchells was here, was the former DuPont mixing guru and is an independent consultant on mixing, and also as an FMP consultant, he would say, "You got the slide 41, it's the first equation you put up?" Okay. Basically, we do have some equations that give us the micro mixing time, the meso mixing time, depending if our flow rate in is really fast compared to the agitator rate, or if the agitator rate overwhelms the feed velocity. And we've got blend time. So the key thing here is that the engineers can go and say, well, what power am I going to put in the plant? Or what power makes sense for this sort of process? We can go and take engineering parameters known as the power number Reynolds number curve. We can estimate the power and think about power in different regions of the tank, or run calculations to estimate power in different regions of the tank. So we can look at the power going into the system, we can look at the flow rate, and we can estimate these times. And this protocol works because, my way of looking at the protocol, feed rate sensitivity, does meso mixing matter or not? Feed location sensitivity, do I get a better process result if I'm dripping on the surface or if I'm feeding to the agitator, where the agitation intensity is highest, where the mixing time will be less for micro mixing and meso mixing? Okay. So that kind of answers Ed Paul's 3 points. Prove otherwise, scale up. Okay, if I go and calculate my lab conditions based on plant estimates of power, I can take scale into account. And then I can go and answer the question whether I need surface feed or not. Okay. This isn't just for reaction systems. The chapter that Cheryl Teich and I have in Advances in Industrial Mixing talk about a reactive precipitation, reactive crystallization, where using the Bourne protocol, we could identify the scale-related sensitivities that we had meso mixing control for that particular system. In addition, recently I had talked about a coagulation or agglomeration process, where if you think about adding an acid or a base to a system that could coagulate, you can go and use this protocol in such a way to enable appropriate scale studies, small scale studies, to resolve production issues. And the benefit of the protocol is you're using the real process. You're not relying on doing extra experiments with a model reaction system. It's efficient, you can step out if there's no sensitivity, and it can be adapted for flow systems also, something I'm working on. And the sanitized process didn't have the benefit of this protocol when that work was done in the early 1990s. The sanitized process would have gotten to the better answer sooner if we had known about and used the Bourne protocol. All right, so where do we go from here? Well, what I want you to consider and take away from this is that if you have competitive, consecutive, or series parallel reactions, or competitive reactions where reaction rates can differ, they could be mixing sensitive. Multi-phase systems could definitely be mixing sensitive. And if we use the protocol We can understand the mixing sensitivities early in process development. You could do these things at the 1 liter scale and draw some inferences on what goes on at the large scale. It gets around the issues of proving that there's a mixing problem or not, scale up making it worse, and you can do the factor settings based on plant conditions. Again, process development is a dialogue between disciplines, having the engineers and chemists looking at the sanitized process that I talked about and coming to some conclusion about, hey, this is something that we should go and study a little bit differently, was an important feature in that. What's next for me on this is I'm trying to figure out, and I'm working with some clients on, how to characterize this micro-mixing, meso-mixing space for better scaling, and I'll have a paper on that at the AICHE National Meeting in November. And with that, I'll stop and go on about whatever else you want me to talk about mixing on, or process on. Sir?
So I guess my question is, you have situations on occasion where you'll have two-phase flow,
Mm-hmm.
and you might be in a region which is mass transfer control, and it might be in a region which is kinetic control. And in case of kinetic control, how well will you work? Because if you're kinetic control, you can mix till the cows come home.
And it doesn't do a
And it doesn't do a damn thing.
That's right. But let's think about with a multi-phase system. And when I teach the course on scaling and piloting, I say to people, all right, well, if you want to get the rates right and drive yourself away from any sort of mixing sensitivity, fine, beat it up. Oh, but in the case we had with the sanitized process, what do you suppose the next step in the process was after we went and had a two-phase mixture and we were going to do that second acylation reaction? It was a phase separation. If I've gone and beaten up a liquid-liquid dispersion to such a point where I make an emulsion, it's very difficult to separate. So we always, and what am I talking about here? I'm talking about reactive mixing. But if you think about reactive mixing just for the sake of mixing, it's not going to get you the answer that's going to be best for your overall process. You have to look upstream and downstream, okay? And you also, in some instances, need to consider recycle carefully, because for multi-phase systems, liquid-liquid systems, some recycle streams can have some surface activity that can go and either give you larger or smaller drops that become more challenging to separate or not, okay? So you have to look at it in the entire process context. So in general, would I want to be in a micro-mixing control regime where flows don't necessarily matter? Sure. Some ways you could go and study that. Look at relative volume fractions of the aqueous and organic phases for your two-phase mixture. And if you go and do that, then you can say, well, wait a minute, is this a kinetic limitation or is this a surface area controlled limitation? And that becomes the key to understanding where you are for the multi-phase system. Did that capture what you were looking
absolutely.
for? Okay. Any other thought? Ron?
So it's, in my experience, very generally, it seems to me that a lot of, maybe the majority of organic reactions would have a half-life on the order of hours.
Why do they have a half-life on the order of hours?
That's what the rate constant is.
That's the conditions that we've chosen to run it at.
Right.
Because
And
many
it's particular
times
temperature.
in the laboratory, I'll eventually let you ask your question.
Okay, thank you.
But when someone goes and develops a route or a compound to see if it has efficacy, whether it's pharmaceutical or agricultural efficacy, very often you're just interested in that one molecule. You want things to be pure. You will actually go and run things more dilute, that when the engineers get their hands on it, they go, we can't afford this. And so the engineers go and say, can you run more concentrated? And so now, if things are a function of, I've had the simple rate expression up there. If they are a function of the local concentration, then all of a sudden I am pushing things faster. So yeah, I've had reaction systems that take forever, okay? And yes, I've had reaction systems where you're looking at fast competitive rates on the order of what I had up there for that second Born reaction. So partially, The rates and reaction times you have are somewhat of a function of the conditions that are being chosen in the laboratory. So sorry, I interrupted your question. Go ahead.
Yeah. So, yeah, I mean, you're absolutely right. You know, if you can run a reaction without heating or cooling, it's about ambient temperature, and it's not exothermic. If the reaction has a half-life of about an hour, and the mixing is a couple seconds, and it seems like the mixing.
You're golden. It's that rule of 1,000, or it's that observation of 1,000. There are no rules other than, you know, what Ed Paul said. But it's that observation of 1,000. If it's 1,000 times faster, don't worry about it. But be conscious of the fact that as you increase concentration, or if you try to go and say, well, how much of an exotherm is there really? Well, if there's no exotherm, if there are no heat effects, that makes life much easier, because as we scale up, we lose surface to volume ratio. Very often we have to have colder jackets than what we have, and that could cause us other sorts of problems. We could even have hot spots where we're adding materials. If I'm doing a simple batch reaction, well, chances are you will have a much longer reaction time than your mixing time. You're absolutely right. The question is there multifunctionality that could be a function of locally high concentrations? And when you get around to the process economics, are we going to want to push the concentrations involved that are going to both push the energetics and also potentially push the byproduct formation?
Okay.
All right.
Okay, this is a hell of a lot simpler. I don't know the answer to it. We are looking at, let's say, introducing a neutralizer into a hydrocarbon stream.
Mm-hmm.
All right, so the question comes up in one, where should the damn pool be put in? Okay, and what position should it be in? And second, what's the role of the static mixer and how the hell do you evaluate it?
Okay. Static mixers, which I stuck to stirred tanks because in the laboratory
No,
we
I
usually have
understand.
stirred tanks. But a
You got
static
chemists
mixer.
here, okay, they don't know
Yeah.
about static mixers.
So if you have a static mixer, then the flow rate and the diameter and the design of the stuff that you've put in the pipe to give it some tortuous path, that's what's putting the energy in.
Right.
That's what's putting the power in. That's what's going to make the micro mixing or meso mixing faster.
There's micro and meso mixing.
In your case, where you're doing a neutralization, it's a fast reaction. You
Okay.
could have some other things going on.
Right.
If it's depending on the nature of the hydrocarbon, and if it's subject to acid or base hydrolysis, whichever way you have going on, then you could go and potentially have some hydrolysis going on if you're not well distributed, if you have locally high concentrations. On the other hand, you might just want to be saying, yeah, I just want to link the pipe and I want to be blended at the end.
Right.
Okay? And so you could do some simple experiments in the lab with a stirred tank, and you could do some flow experiments with a pipe and a static mixer in it at different flow rates. You can adapt this protocol to look at different diameter, different length, different flow rate. And you could also look at where I add the material. In a pipe, just like I've got the top of the tank and the impeller, with a pipe I have some choices also. I can go and add to the edge of the pipe, and if I had no static mixer in there, and depending on my flow rates, maybe things just run along the top of the edge of the pipe.
Right.
Or maybe I could add it to the center if I put a tube with a little L in there, and that can inject along the streamline.
Right.
That may do better if you have a turbulent system. But then if you have some material inside the static mixing elements, in general, feeding to the center can have some greater benefit. And maybe even feeding a little bit downstream of where the static mixer starts. Okay? But some of it depends on your rheology. It sounds like you're looking at low viscosity systems.
Right.
And so you're probably okay with a centerline injection, and depending on what flow rate you're at. You're going to be
pointed
turbulent.
upstream.
I've got my static mixer and it's this long,
Yeah,
and it starts here.
yeah.
Maybe I put my injection point just after the start of the static mixer.
Just at the start, okay.
Okay? And that kind of lets the flow develop in the static mixer, because depending on what you have upstream, you might have some structures to your flow that aren't fully developed. Okay? So if you've got elbows or something right before the injection point, you know, maybe you want to be a little upstream, so you let a little bit downstream at the beginning of the static mixer, so you let the flow develop a little bit before you inject.
Okay.
Okay.
Second question.
Second question, and then we have somebody online.
Summarize your questions if you
Take them
will.
first.
Thank you, yes. The question was if I had a static mixer or if I was neutralizing a hydrocarbon stream and a static mixer system, how do we go and deal with that? Okay.
The second one was on viscosity. I'm just thinking here about, that I'm doing painting the house, I'm just mixing, okay? So the fact is, I'm looking at a viscosity system. All right, now, I'm thinking lightning, okay, on the point. But the viscosity would seem like it would be would have quite an effect on your mixing.
Absolutely, and the rheology of paint is fascinating, okay? The question is, if I'm mixing paint in a can,
Say a 5-gallon bucket.
let's say a 5-gallon bucket, what's the challenges? Well, just think about the poor people who had to make the paint to begin with, who were adding pigments and adding, you know, different extenders and other things in there, and the challenges they have. And the fact is, water has the same viscosity no matter how much you beat it up, okay? Paint is cool. Because you take a paintbrush and you stick it in the can and you take the paintbrush out, you don't want that paint dripping off until you go and put it on the wall. And you want it to spread on the wall nice and uniformly. While I apply a shear rate or shear stress to it, I want it to spread out. I want it to have low viscosity. But when I take my brush away, I want it to sit there, such that when there's no shear rate acting on it, it doesn't move. It's a shear thinning fluid, which creates some interesting challenges when you look at those sorts of systems I was showing there, those blend time type of videos. If I go and have a shear thinning fluid, the highest shear rates are right around the impeller, and sometimes it can take longer to mix depending on how shear thinning a fluid is. Stuff away from the agitator will have a higher viscosity than the stuff nearer the agitator. So it creates an issue for people who make paints and people who, in your case, mix a 5-gallon bucket of paint. Just keep in mind that where your stirrer is, or where your little drill bit is, the viscosity is going to be really low there. There are some paint manufacturers who actually have tanks where they can move the agitator up and down as they're processing.
Oh, I move it up and down when I mix it.
Yeah, yeah, and because you want to make sure that all regions of the tank move.
Don't want to have it offset?
Offset is good because you do not have baffles in a bucket. Okay, so move it maybe a third of the way to the wall.
Okay.
Okay, and that will help set up good flow patterns.
Okay, good. I'm baffled by this particular explanation, but I think I can.
show you some cool diagrams, but yeah, that's neat.
Thank you.
Okay, anything, there was one, what the comment from online was, repeat the question, right?
No, that was just mine too.
That was yours too, okay. Is there
Yeah.
anything from online that
Attendees, but they're listening intensely, not commenting.
They're all mixed up by my explanation. There are no good mixing jokes, by the way. Any other questions or thoughts? Keith?
Curious, Aaron, whether you've had much experience with biologicals or the sorts of, like Pyro and I have had to work a lot with suspensions, really awful ones. We always try to push our percent solids up when we're doing biomass conversion from like as high as we can get it to make the economics good. but sometimes we have shear sensitive cells. We'd like to mix the beans out of it, but it costs money. And sometimes the cells don't take to that kind of shear force well.
And I'll bet these cells want to breathe too.
Sometimes yes, sometimes no.
Okay.
Sometimes they're anaerobic.
So just like if I want to go and get kinetically controlled systems with liquid-liquid, if I want to get the most gas into a system that I want, if I want it to be saturated, I beat the heck out of it. But the bugs tend not to like that. It tends to make them, well, kind of like bugs squished on the rug. One thing to consider in terms of biological systems, pushing them to higher productivity and not going and breaking them apart, okay? Not breaking them apart before you want to break them apart, if indeed that's what you're going to do. Well, let me put it this way. I once worked with somebody on a polymerization system where they said, oh, this is shear sensitive. You can't stir it any more intensely than you are here. And we're going to make it in this thimble scale, and then the shot glass scale, and then the, pint of beer scale, and then we're going to put it into a 1 foot diameter tank, and eventually we're going to go to a 2,000 gallon tank. But so help me, don't beat this up more than it would have if it was in a roller bottle. Well, what happens when you increase the speed? Oh, that's bad. Well, how much room do you have to work with? Well, we have to make it exactly the same. Well, you can't.
Right.
So my question with these biological systems is, how much intensity can the system tolerate?
Yeah.
And that's where this sort of protocol kind of makes sense. Maybe I don't do the 100-fold difference in power, but just how much energy can this system tolerate? Because what you end up seeing, you'll see the yield of whatever you want to get out of this bug or cell go down if you go and beat it up too much. But you'll actually see it come up because you had better nutrient flow or respiration or whatever you want to say. There will be some optimum, okay? And there can be completely different mechanisms about why your yield of your desired material fell off.
We sometimes are working at 50% solids.
Yeah, and the rheology you have is probably awful because just like the latex paint, you may very well have a system that is shear thinning. Some systems are just the opposite, like, not that you use clays in your biologic system, but a clay goes the other way. You apply shear, it will thicken, okay? So one thing to suggest when you go and look at systems that have biologics in there, number one, understand the rheology. Well, how do I do that? Well, you take a little viscometer that has spinning, a cone and plate or a, concentric cylinders, and you rotate it at different RPMs, and you take your viscosity readings. And then there's a shear rate that's associated with that. And you'll see your viscosity go down as your RPMs go up. Okay, cool. At what RPM did your bugs die? And so if there's some way to go and make some physical observations or go and take that sample and put it into your system and then say, well, what sort of yield do I get now after these bugs have been sheared at this shear rate? Then we can go and say, all right, here's the type of environment that these can tolerate. And there's a big distribution of shear rates and shear stresses in a stirred tank, okay?
Yep.
So that could dictate what type of agitator we use. That could dictate how many agitators we use and what sort of agitator speeds do we go at. So again, you can learn a lot from a little bit of a rheology study. But you're kind of in a box. You want the good gas liquid mass transfer, perhaps, and you're kind of stuck on the other side because you can't go intense enough or too intensely to break the bugs.
Right.
Yeah.
How does the shape of your reaction vessel affect the efficiency of your mixing? The video you showed earlier was a cylindrical container. As these reactions grow in size, I presume the reactors are more cylindrical or spherical in shape.
Not necessarily. In fact, this particular example with the 1-to-1 aspect ratio, it's kind of the basis that academics have gone and used for studying mixing. People like FMP, who I probably, if I didn't say, I should say, they're the world's premier mixing research group that does things that's industrially relevant. They've gone and looked at different height to diameter ratios, different base shapes, okay? Other people have done that too. Thing of it is, if you have an Aaron-shaped reactor as opposed to a short fat reactor, now all of a sudden maybe I need multiple agitators in there to completely move the contents, okay? And that creates a different sort of scaling issue. You're not necessarily going to something more spherical in terms of these types of stirred tanks. In fact, if you talk to people in the pharma industry who are going to contract manufacturers, or in the ag industry, or any of the industries that go to contract manufacturers, you're seeing stirred tanks that might have an aspect ratio of 1.25 to 1, okay? So 1.25 times higher than their diameter. So really, that's not necessarily an issue. Now, there are some very interesting things. If a tank is physically square, has square corners, there are some interesting things in terms of spherical types of vessels. Years ago at Roman House, we actually did a paper on power dissipation in a round bottom flask, a 5-liter round bottom flask at one of the mixing conferences. And people at first laughed about it and then said, well, that's really neat, no one's done that, you know. So there are some differences in terms of geometry, but you're still putting in a certain amount of power. You're certainly taking a certain amount of time to blend. You're still going to have a feed plume. So the type of construct we're talking about and the type of variables, the factors and the responses that are important for your process can still be studied and characterized, and then you can still take the large-scale system, design the small-scale experiments appropriately. So, anything else?
If not, let's thank Aaron for a great talk.
Please leave your badges. Wait on here.
Sir?
Stick them right there.
Fantastic talk. Oh, thank you. Mixing has been a bugaboo for every chemical engineer. Sometimes you don't realize it until it's too late.
Oh, the thing of it is, we learned this in Leavenworth.
Yeah. Assume it's not a problem.
Yeah,
So therefore it's not.
and now it's the exact opposite. Whether you have